Hi everyone, my name is Chen Hao and today is the first video of my series on integration techniques in physics. So the goal of my series is to try to explain how to do multivariate integral like that appears in electromagnetism, your moment of inertia calculations, or your potential energy calculations. So in the first video of this series, I'll be talking about basic integration techniques, and specifically I'll be focusing on the integrals that are more relevant to physics. So I'll be covering 3 integration techniques. The first one is called just memorize, where there's not much special technique to it. You kind of just have to memorize a step. The second will be integration by parts, right, which appears in some physics questions, but it's not all that common. And the last one will be U-Substitution, which is very, very common in physics calculations, especially trigonometric substitutions. Then the following videos will be covering things like 1D integrals, 2D integrals, 3D integrals, as well as surface and volume integrals before applying them to physical applications. So without further ado, let's begin with the first technique. Just memorize. So for some integrals, there's not much trick to it. You just kind of have to memorize how to do it. So an example would be integral of secant of x with respect to dx. In this case, you have to multiply by 1 in a very special way, and specifically, you have to multiply by 1 as the fraction of secant x plus tangent x over secant x plus tangent x. Even though this quantity is simply just 1 and it seems redundant, but actually if we expand down, we realize that this takes the form of logarithm. So if I expand secant x over the numerator, we'll get integral of secant squared x plus secant x tangent x in the numerator. And the denominator stays the same, except that I'm going to write it as tangent x plus secant x now, dx. And the reason why I do this is because we can observe that the derivative of tangent x is secant squared x, and the derivative of secant x is secant x tangent x. So this takes the form of integral of f prime of x over f of x dx, where f of x is equals to tangent x plus secant x. And we know that the integral of this form is logarithm of f of x plus c. Don't forget the absolute sign is important. Substituting f of x back in, we get logarithm of secant x plus tangent x plus c, where c is arbitrary constant. Okay, so that's how we do the first integral here. Now, without knowing ahead of time that if to multiply by 1 in this unique way, it's quite difficult to arrive at the result. But if you knew the result like that already, then it's easier to motivate multiplying by this quantity over here. For another example, if we have integral of secant squared x dx, in my personal opinion, the easiest way to do this integral is tangent of x plus c. I feel like this is one of the integrals that are worth memorizing, and in general, this is a pattern you see across your integral calculations. There's going to be some quantities that are worth memorizing and some quantities that are not worth memorizing, and you should derive them on the spot. It's up to you to strike a balance between memorizing the integrals versus deriving them, or knowing how to derive them. There's a few more examples of just memorize integrals, but I think these are the ones that are more common for physics. So now we move on to the second part of integration techniques, which is integral by parts. Integral by parts is essentially the reverse of the product rule. In other words, we take the product rule, which tells you that the derivative of product of two functions u and v is equals to u prime v plus u v prime. If we integrate both sides of this expression of the product rule, we'll get integral by parts. So there's kind of two scenarios over here. One is a case where doing a definite integral. In that case, the definite integral from a to b on both sides of this would yield uv evaluated at b minus evaluated at a equals to integral from a to b u prime v dx plus integral from a to b u v prime dx. Knowing that u prime equals to du over dx, we can write u prime dx as du, and likewise we can write v prime dx as dv. And rearranging this expression will give us integral of u dv is equals to uv evaluated at endpoints minus integral from a to b of v du. Now, if you don't like this dv over here, you can think of it as a function f dx. So having dv is equals to f dx, or alternatively, v is equals to integral of f dx. Then the integral by parts formula will take the following form of integral from a to b of a function g times f dx is equals to evaluated at the endpoints g integral of f dx from a to b minus integral from a to b of this v quantity would be integral of f dx. So integral of f dx. This du over here, right, in our case u being g, would be dg over dx multiplied by dx. Loosely speaking, you can kind of think of this as a cancellation of the dx or introduction of dx. And although this is not rigorous at a high school level, it is rigorous at a uni level where we talk about differential forms. However, this is an advanced topic which I'll probably talk at the end of this series, but for now, you don't need to think about it. Now, whether you memorize this form of integral by parts or this form of integral by parts, it's completely up to you. Personally, I like to remember the latter because I use a mnemonic to remember how to do integral by parts. But once again, it's completely up to you. It's your personal preference, and usually you find your personal preference by doing a lot of integral by parts exercises. So that's what I encourage you to do. Do a lot of exercises, grind the exercises, and after a while, you'll find what works best for you. Now I'll share my mnemonic that I use to memorize integration by parts. But before that, I like to emphasize something, which is that when I do this integral over here of f dx, this integral of f dx doesn't come with a plus c. Right? This integral is actually an anti-derivative. It might be misleading to write this as an integral because one might think that if for example f is 2x, right, then integral of f dx might be x squared plus c. But in this case, this doesn't have the plus c. Okay, it shouldn't have the plus c. And so perhaps in this way, the dv notation over here and v over here might be more appropriate because it doesn't have this misleading integral which doesn't actually have a plus c. So this is one possible pro of using the first method over the second method, right? But once again, I still choose to use the second method as long as I'm aware that this integral inside here doesn't actually come with a plus c. If it did, then you have two integration constants, two arbitrary constants, which is not right for a single integral. So what is this mnemonic that I like to memorize? I like to think of it as integrate keep minus integral of integrate differentiate. So if I might draw your attention to the bottom left over here, whenever I take an integral of something, that the integrand can be written as a product of two functions. I like to think of one of them as the guy that I'm going to integrate. So for example, in this case, I'm choosing f to be the guy that I'm going to integrate all the time. And the other function is going to be the guy that is kept the same for one term and is differentiated for the other term. So by the mnemonic that I use, the integral of f times g dx is equals to integrate keep, which means that I integrate my function f dx without the plus c, and then keep means I multiply by g and I don't do anything with it, right? So I keep it the same. So the first term, once again, is integrate keep, and this term is evaluated on the endpoints a to b, and then I minus away, right, which is in the mnemonic. I subtract away the integral from a to b, the same bounds, the integral, right, which is the fourth term, of integrate differentiate. So once again, integrate means I integrate f, and differentiate means I differentiate g, right? And lastly, we're performing this integral with respect to dx. Okay. So if I put it all in one line, once again, whenever I integrate the product of two functions, right, f and g, I choose one term which I'm going to purely integrate, and I choose the other function which is multiplied by g would be something that I keep for one term and differentiate for the other. So I memorize it by integral of parts of this fg with respect to dx is equals to integrate keep minus integral of, which is this integral of from a to b of integrate differentiate. Okay, so that's just how I personally memorize it. This is what works for me. But once again, if you don't want to adopt my method or you find it too confusing, you can grind a few exercises and chances are that you come up with your own personal way of memorizing. This is my shortcut of memorizing without having to derive it every single time. Perhaps you can think of it as u dv is equals to uv minus integral of v du, right? That might work for you. But for me, when I think of dv going to v, for me that's a bit confusing. So I prefer to think of going from dv to v as the integral, right? Which is what the integral of f is over here. So later we'll go through a few examples of this being used in practice. And I think at this point, it's useful to emphasize what partial integration is useful for. So partial integration is useful if you have a function that's difficult to integrate, like g, but you have another function that's easy to integrate, like f. Right? Remember, we're integrating f, and we don't integrate g. So only in one term we're keeping g, and the other term we're differentiating g. And we know differentiating is something we can do very algorithmically. There's a formula, there's a series of rules to differentiate any differentiable function out there. So g can easily be kept alone or differentiated, and the integral we need to do is this integration of f. So if we choose f to be a wise function that is easy to integrate, then we can do this integral over here, and the hope is that when we differentiate g over here with respect to x, right, it makes g easier to integrate. Of course, there's this factor of integral of f dx over here, so that might make the combined expression, the combined integrand in the second term, a bit difficult to integrate, but at least there is some hope in being able to do this integral without needing to integrate g. Or another way to think of partial integration is if the combined f and g is difficult to integrate, but you kind of know how to do calculus with each one of them individually. So an example of that kind of scenario would be if f is cosine of x and g is x squared. So if you don't know how to integrate these two together when they are multiplied together, but you kind of know how to do calculus with each one of them individually, then you can apply integral by parts. Because when we differentiate g, right, the polynomial power over here drops by 1. So x squared becomes 2x, and then it becomes 2, and eventually becomes 0. So we can apply integral by parts repeatedly to lower the power of x. And when it becomes trivial, then since we can integrate cosine of x infinitely many times, right, it just toggles between cosine and sine, we can iteratively apply integral by parts twice to integrate this product of these two functions. So once again, integration in general is easy, right? The integral by parts rule is something you can try in a lot of integrals, but there's no guarantee, and usually it comes with experience whether you should use which technique for integration. So I've shared my personal way of memorizing integral by parts, and for the indefinite integral, right, it's simply the same thing, but you have a plus c at the end, right? Once again, remember that the integral of f dx over here does not include a plus c, right? If you did include a plus c, then you have two arbitrary constants, which is not right if you just perform a single integral. So let's go through a few simple exercises. If I have integral of logarithm of x dx, even though logarithm of x seems like a single function, and it's a function that we don't really know how to differentiate at the moment, we can think of logarithm of x as 1 times logarithm of x. So in this case, my function f is 1, and my function g is logarithm of x. So remember, g is the function that we don't really know how to integrate, but we know how to differentiate it. Indeed, we know how to differentiate g. So applying my personal mnemonic over here to this example, the integral of a product of two functions 1 times ln of x is integrate 1, which is just x, keep g, which is just ln x, minus integral of integrate 1 once again, which is x, and differentiate ln x, which is 1 over x, and then integrate this with respect to dx. This is then x ln x minus integral of 1, which is x, and we have a plus c, where c is an arbitrary constant. So 1 is the function that I integrated, and ln x is the function that I keep and I differentiate. Okay, so integral of 1 times ln x dx is equals to integrate keep minus integral of integrate differentiate. Okay, so that's how I see it. Another example we can try is integral of x ln dx. So in this case, the function that I'll be integrating will be x, and the function that I'll be differentiating is ln of x. So integral of x ln x dx is equals to integrate keep minus integral of integrate differentiate. First term stays the same, second term can be evaluated, e squared over 4, and lastly, not forgetting the plus c. So color coding the parts that I've integrated and kept and differentiated, you can see that my mnemonic is integrate keep minus integral of integrate differentiate. Okay, so I hope these examples have come in handy. I'll encourage you to try more examples. I chose these two examples because they might appear in physics, and a lot of integral by parts examples that you see out there will almost never appear in physics, and I try to stick to the physically relevant examples. But if you want to master partial integration, you should try out all the math examples, even though they might not have relevance to physics, just for the sake of getting used to it. Okay, another interesting example would be one that requires rearrangement. So there's this H3 physics question where you need to find the tension in the string, and after all the physical setup, it boils down to evaluating this integral. You can watch the video over here where I talk about it in greater detail, but this is essentially one of the sanity checks we can perform to make sure our answer is correct. So in this case, how do we evaluate this fancy integral? The integral from 0 to pi over 2 of some constant t0 times e to the mu theta, mu sine theta plus cosine theta, d theta. I expanded the whiteboard so I have more space because this is going to be quite a lengthy calculation, right? And I choose a guy I'm going to keep or differentiate. So in this case, I'm going to integrate e to the mu theta, and I'm going to keep or differentiate mu sine theta plus cosine theta. You might recognize this from the capstans equation, but you can check out the video for more details. So I'm going to call this integral I for reasons you'll see later. But if we try to perform integral by parts once, we'll get that this is integrate keep minus integral of integrate differentiate. And because this is a definite integral from 0 to 2 pi, we need to evaluate the first term at the boundary, and the second term is a definite integral. So if we substitute in the two bounds, right, pi over 2 into this expression, we're going to get t naught e to the pi over 2 mu over mu times mu, and then cosine of pi over 2 is 0, right? Then we're going to subtract away this expression, evaluate theta equals to 0. So that'll be t naught e to the 0 is just 1, and this is 1 over mu, and sine of 0 is 0, cosine of 0 is 1. So this is the first boundary term, and we're going to apply integral by parts to this guy again. So it's going to be, this guy is the one that's going to be integrated, and this guy is the one that's going to be differentiated. So there's going to be integrate, keep, minus integral of integrate, differentiate. Right? And once again, it's a definite integral, so the first term must be evaluated at the endpoints, and the second term is a definite integral. Simplifying down the first expression, we're going to get t naught e to the mu pi over 2 minus t naught 1 over mu, and subtract away the thing in the massive round bracket, t naught e to the pi over 2 times mu over mu squared minus 1, right? Because cosine of theta is 0 at pi over 2 and sine of theta is 1, and then we subtract away t naught e to the 0, which is 1 over mu squared times mu, right? And we minus away this term. But what's interesting is that we observe that this giant term over here is actually proportional to our original integral I. And the reason is because when we integrate e to the mu theta twice, we put out a factor of 1 over mu squared. And when we differentiated mu sine theta plus cosine theta twice, we put out a factor of minus 1. So essentially, the whole thing in purple over here, last expression, is just minus 1 over mu squared times I. And this at first might seem concerning, because it seems like when we try to evaluate the integral I, we get back I, which means that we kind of need to apply integral by parts infinitely many times in a very recursive manner. However, similar to how when we do resistor questions where there's infinitely many resistors, what we actually do is we actually say the whole effective resistance is some unknown, and then we substitute it into itself and get a self-consistency equation, right? Applying that same procedure, we can say that I must be equals to this thing on the right hand side, but a giant thing, right, it's just a self-consistency equation for I. So if we can rearrange this expression and make I the subject of the formula, then we have effectively solved for I. So all that's left to do is to simplify this expression down. So the first term is just stays the same, and so this term is going to be plus t naught e to the mu pi over 2 1 over mu squared, and this minus sign distributes over again with t naught 1 over mu. And lastly, we subtract away, right, distributing the minus sign, being very careful with the minus signs. We see that this term and this term cancels. These two terms can be factorized as t naught e to the mu pi over 2 times 1 plus 1 over mu squared, and the last term stays the same, and the left hand side is I. So now moving this term over to the left hand side, we get that I times 1 plus 1 over mu squared is equals to t naught e to the mu 1 plus 1 over mu squared. And now we are rejoicing because we can just get the common factor of 1 plus 1 over mu squared to obtain I is equals to t naught e to the mu pi over 2. So this kind of trick is common when we talk about integrals of exponential function times a trigo function, because of the fact that when we do integral of these quantities twice, or we differentiate it twice, it picks up a scaling factor, meaning either it picks up this exponential term over here or picks up a minus sign. And of course, this kind of hints a bit at the relation between exponential and trigonometric sine and cosine functions, right? Using the Euler's formula, e to the I theta is equals to cosine theta plus I sine theta, right? There's some relation with this, right, which one can dig into. But in the context of integral by parts, what we're concerned with here is that when I evaluate this kind of integral, I can express it as I equals to something 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 times I, right? And this way, if I make I the subject of the formula, similar to that of the resistor questions where R effective is equals to something something some function of R effective, and then this self-consistency equation, rearrange it, we find R effective. Likewise, we perform the similar procedure, we get the integral I is this expression. Okay, and with that, we come to the end of the integral by parts section. Now, before I move on to the next section, I'd like to talk about something a little bit extra, which is Noether's theorem. Even though integral by parts isn't commonly used in calculations of exact systems, of physical systems, it's very, very, very prevalent in Noether's theorem. It's very, very commonly used in the derivation of conserved quantities. I shared some intuition and talked about Noether's theorem in this video over here. Lagrangian mechanics is an infinite dimensional vector calculus, right? And I'll talk about it in this lecture in greater detail. But roughly speaking, Noether's theorem tells you that every conserved quantity arises from some continuous symmetry of the system. And typically, in the derivation of this Noether's conserved quantity, right? In the derivation of this conserved quantity, like momentum, energy, or angular momentum, in the derivation of this, we use integral by parts. And so what it usually looks like is that we usually have something like saying that integral of j of x derivative of some epsilon of x dx. We usually say that this entire thing is equal to 0. So for all functions, right? All functions. And we use integral by parts in this scenario to say that this is equals to some boundary term, which is usually cancelled, minus integral of derivative of j times epsilon of x. So essentially, in Noether's theorem, in the derivation of Noether's theorem, we often use integral by parts to move this derivative operator, right? Usually it's a multivariate operator, but it can be single variate as well. We usually use it to move this over to the other quantity over here. And then when we say that this entire thing is, since this thing is equal to 0, for all functions e of x, that would imply that the derivative of j is 0. And this is what we call a conserved current. So I think this example is really cool because this permeates a lot of theoretical physics, right? This procedure is very common in field theory, and it can help us get very useful quantities. And this Noether's trick, right? This is what we call Noether's trick. This Noether's trick is really very, very useful in deriving our conserved quantities. And integral by parts play a crucial role over here, right? We do partial integration when we move the derivative from my epsilon, right, to the j. And so we can transfer the derivative to the other guy, and that's a very useful procedure in physics. You also often see this used in theoretical physics as something like d phi, right? Usually we see something like that. This is actually d phi squared, some kinetic term. And usually when we integrate by parts, right, under the integral, when we integrate both sides by parts, we translate this into integral of phi d squared phi. And we like this because, not forgetting the minus sign over here, we like this because this expression looks a lot like a matrix. So this looks a lot like v dot av. Okay, that brings us to talks about Green's functions, right, which are essentially inverses of differential operators. But that's a very interesting topic for another time. If you want me to talk more about it, please DM me, right, on Telegram, or you can leave a comment in the comment section below, and I'll make a video on this very interesting topic. So integral by parts, maybe not so useful in physics Olympiad, but very, very useful in theoretical physics. So I hope that has piqued your interest a little. And now it's time to move on to U-substitution. So the common U-substitution we perform in physics, at least for electromagnetism, is trigonometric substitutions. And so besides covering the analytic calculations, right, which are often quite detailed and long, I also want to talk a bit about the geometric interpretation of U-substitution. And this also coming nicely next, line integrals. When we talk about line integral, it turns out that U-substitution is just a reparametrization of a line integral. Right? But more on that next week. For now, U-substitution can be thought of as a convenient way of simplifying integrals. And how it's usually done is we make a choice of how to rewrite the variable of integration. So as an example, if I'm evaluating the integral of dx over square root of x squared plus a squared, the variable that I'm integrating over right now is x. And I can make a substitution of x equals to a tangent theta, such that now instead of x being the variable I'm integrating over, it's going to be theta. And a is just a constant, right? So in order to do that, I need to find out what is the derivative of x with respect to theta. In this case, it's just a secant squared theta. So moving theta to the other side, we get a secant squared theta d theta. So these two expressions are going to be the ones we substitute into the integral we're trying to perform. So substituting in dx into here and x into the denominator, we get that this is integral of a secant squared theta d theta over square root of a squared tangent squared theta plus a squared. And if we simplify this, we can make use of the fact that tangent squared plus 1 equals to secant squared, right? And if you have trouble memorizing this, then you can always remember that we can take the sine squared plus cosine squared equals to 1 and divide both sides by cosine squared, right? So using this trigonometric identity, we can get this is equals to a secant squared d theta over a secant theta. So this is equals to integral of absolute of secant theta. And this integral is something we know. By making a choice that x equals to a tangent theta, we have reframed this integral to an integral in terms of theta. So I want to draw an analogy with the summation, right? Let's say I'm sum over from k equals to 1 to k equals to 5 of 1 over k squared. If I change the variable of integration from k to j, and let's say j I set it to be equals to k plus 1, then I can rewrite this as sum from j equals to 0 to j equals to 4 of 1 over j plus 1 squared. Right? We notice that we're evaluating the same sum, right? We're evaluating the same sum, just that the variable that I'm choosing to represent this sum is different. I go from k to j, and two things must happen. Number one is our expression 1 over k squared must become 1 over j plus 1 squared, right? We cannot have any more mentions of k here. There's no k inside this expression. And the other thing that must happen is that the limits of integration from 1 to 5 must also change from 0 to 4. So this ties in very nicely when we talk about changing the limits when we perform a U-substitution. So let's say instead of doing an indefinite integral like this, we actually want to perform a definite integral from minus b to b, right? As shown in this example. So what we're actually doing over here is we're actually saying sum from x equals to minus b. So this is actually x equals to minus b to x equals to b, right? Where x is the variable that I'm integrating over. And integral is really just like a sum. So when I'm performing this integral, and when I change the variables of integration, I must also change the limits of integration. So how I can perform the change in limits is I can consider two endpoints. So if x equals to a tangent theta, right, then at x equals to minus b, right, that would imply that tangent of theta is equals to minus b over a, or rather theta is equals to tangent inverse of minus b over a. And pulling out the negative sign, I can have minus tangent inverse of b over a. And likewise, the other scenario, the upper bound, right, when I have x equals to a tangent of theta and x is b, then tangent of theta is equals to b over a, and theta is equals to tangent inverse of b over a. Okay, so if I call this thing alpha, if I call this tangent inverse b over a alpha, then after I perform the change in variables from x to theta, I must also correspondingly change the limits of integration to theta equals to minus alpha to alpha. I change my sum from k equals to 1 to k equals to 5 to j equals to 0 to j equals to 4. I must also change the limits of my integration when I change the variable that I'm integrating over, right? So ultimately, U-substitution is just changing the variable that you're using to perform the integral. And in this case, I choose to map the two variables in the following way. We'll see later this is a very nice geometric interpretation when I talk about parametrization of a curve. So I think there's two things that I want to emphasize here when you do U-substitution. Number one, analytically, the integrand changes by performing the two substitutions over here. One for the variable they're integrating over, and the other for the dx, right? You must replace both of them. Every mention of x must be replaced, and the single mention of dx must also be replaced, because you cannot have any more mentions of the old variable. You're changing to a new variable, theta. Everything must be in terms of theta. That's one aspect. The other aspect is that you must change the limits of integration correctly, right? You substitute in the endpoints for x, you find the corresponding value of theta that gives you that value of x, and that's your new limits of integration. If you want to have a deeper understanding of it, refer to the change in variables when you do summation. It's essentially the same procedure, right? The thing we're summing over is analogous to the integrand, and the sum is analogous to the integral, and the bounds over here are the limits of integration. So don't forget these two things, right? If not, you're going to get wrong answers. So in the example we have over here, when we actually perform the integral, right, we get integral of absolute of secant of theta. And in this example, secant of theta is never negative. So we can drop the absolute sign. So there's no more absolute sign, it's just secant of theta. And we know how to integrate that, right? It's just logarithm of secant theta plus tangent theta. So substituting in the two endpoints minus alpha and alpha, we get this, right? And if you want to evaluate things like secant of tangent inverse of b over a, you can draw a nice triangle. So you draw a triangle, right? If this angle we call theta, tangent inverse of b over a would correspond to this triangle, right? Secant of this quantity, right, by Pythagoras theorem, is just the hypotenuse over the adjacent. So that will give us this here, right? Whenever you want to do Trigo calculations like that, there's a table on Wikipedia, but you don't need to memorize it. Whenever you need to do such things where you do a trigo to an inverse, right, just draw a right angle triangle and label all the necessary sides. So simplifying that down, we get this. So this example of U-substitution has emphasized the various features of it, right? Namely, analytic aspect, the limits of integration aspect, right? And now I want to show you a few more post. But before that, I think it's important that I emphasize a geometric interpretation. When I perform the integral from minus b to b of whatever integrand with respect to dx, this can geometrically be pictured as a line. The evaluation of this integral along some line, right, from x equals to minus b to b. So this x goes in this direction, and essentially along this line, we are associating certain values along the line, right? And along the line, the values are decided by this integrand f. So this integrand f of x determines how much each part of the line contributes. And think of it as a function on the line. If you want a physical analogy, imagine a rod, right? And imagine the f of x tells you the mass of each point on the rod. Right? So the f of x is some mass distribution of the rod. Now when I perform an integral of f dx, I'm kind of like finding the total mass of the rod. But suppose this function f was a bit difficult to integrate. Then I choose a parametrization of x equals to a tangent theta. Now what that would look like geometrically is if we think of x as a point here. So let's say x is a displacement from the center of the rod, right? Then if I draw a perpendicular line out here, and I call this A, then if this place has location x, then this angle is theta, right? Because tangent of theta is x over A. Then what is dx? Dx, right, interpreted in this picture is an infinitesimal element of x. So in this case, dx is actually a small line segment here, dx. In the left diagram over here, this green part is dx, right? Green. This dx, right, if I write it in terms of d theta, is equals to a secant squared theta. This is d theta, right? It's a small change in the variable theta. So, referring to the diagram over here, if I chase the angles out, and of course this is all in the case of a small dx and a small d theta, where everything is kind of linearized and all the curved lines are straight lines. So your arc lengths are like isosceles triangles, right? Your pizzas are kind of like isosceles triangles because for small quantities everything is straight. And so the yellow line over here is a secant theta, right? Because it's the hypotenuse of this right angle triangle. And this isosceles triangle over here, where the yellow and part of this orange line, this isosceles triangle has an arc length of a secant theta d theta. Then from this arc length, tracing a bit of angles, we know that this angle down here, this black angle over here, between the green line and the purple line is also theta. And so the green segment over here, the dx is a secant squared theta d theta, right? So essentially what we have done is we have given a geometric interpretation for the differentials dx and d theta and how they relate to each other, right? It's kind of like saying I want to change the way I describe the rod from a variable x labeling points on the rod to an angle theta describing points on the rod. In this case, if I move x in a small direction dx, if I move x a little bit, I change x a little bit, a small segment dx, it corresponds to d theta but with a weight of a secant squared theta because theta is now the angle. Theta is now the angle that you observe the rod, and the further out you observe, right? The further out you observe, the more your parallax error. This a secant squared theta is kind of like a parallax error. It's kind of like a parallax error when you observe the length. So that's what this a secant squared theta accounts for. And now your differentials dx is written in terms of d theta with this weightage for parallax. And now when we perform the integral, you can now find out the total mass of the rod, right? By using theta as your parametrization, as long as you have made sure that you have your dx changes to some weighted value of d theta, and your x changes correspondingly to the value of theta that gives you the x. So fundamentally, when we perform an integral, we're actually finding the mass of the rod. But there's multiple ways of calculating the mass of the rod. If you're on the rod, you can walk along the rod and measure each segment dx, how heavy it weighs, with a weight weighted by f of x. You walk along the rod, measure how heavy it is, and you sum it up. But if you're a far observer, if you are standing at distance a away from it, you're a far observer, the only thing you can vary in some sense is your angle theta. And you look at, at theta equals to 1 radian, it is how heavy. Theta equals to 2 radian, it is how heavy, right? And essentially, U-substitution is performing this change in perspective. And this will tie in even more closely next week when we talk about parametrization of a curve. When we talk about parametrization of a curve, you realize that U-substitution is just a re-parametrization from the parameter x to the parameter theta. So that is something that will be useful insight for U-substitution and a lot of physics questions. When we perform a U-substitution, sometimes performing this trigonometric substitution it really makes sense what's going on in the context of this geometric picture, okay? Especially when you're doing things like finding the total mass of some object, right? You realize, oh, U-substitution analytically, mathematically is some change in variables, some change in limits, but geometrically, I'm just looking at the object and describing the object in a different way. So with that out of the way, right, that geometric picture is very useful. I recommend you guys try to internalize it. But to close off, we'll just go through some simple examples, right? This shouldn't be too long. If we have integral of dx over x squared plus a squared, then we can use the same trigonometric substitution, but now the integrand, instead of being secant of theta, right? Just now the integrand here was secant of theta, now the integrand is just 1, right? And hence, this is our answer. And lastly, if we do integration of dx over square root of x squared plus a squared cubed, right? So this is x squared plus a squared to the power of minus 3 over 2. If we do this integration, then we use the same substitution, right? Because the denominator kind of stays the same form, right? The x squared plus a squared stays the same, right? But now we get essentially cosine theta instead of secant theta or 1, right? And hence, when we perform the integration, we'll get this. So the reason why I emphasize these three examples is because this integral is kind of like integral of potential along some line, right? If you have some line charge, then if you stand a distance a away from it, and x is a parameter describing where you are on the line charge, then the distance is going to be square root of x squared plus a squared. So this distance I'll call r. Then this integral is kind of like a 1 over r integral, right? And 1 over r, if you know electric potential, V is proportional to some constants times 1 over r. So that is kind of like finding the total potential at this point, right? But we'll talk more about it when we talk about electrostatics. So 1 over r integral, the first example we went through, it kind of like calculation of potential energy, right? But I phrased it purely mathematically, so we don't need to talk about any physics at the moment, right? All this is just purely mathematics. 1 over r squared, not very common, right? But we did it anyway because it's a good in-between. 1 over r cube integrals is kind of like your electric fields, right? If you want to find the total field strength at a certain point, total electric field, which is a vector, then it turns out your integral is something of this form. You may be wondering, wait, isn't electric field 1 over r squared? But the reason why I say it's 1 over r cube is because, yes, it's 1 over r squared for the magnitude of it, but the direction changes as well. So as your angle, where you are on the line, not only does it affect the magnitude, right, via the distance, via 1 over r squared, it also affects the angle, right? The angle of your vector changes also with respect to angle theta. And turns out the dependence will be this exponent of minus 3 over 2. Okay, so we have covered the basic integration techniques. In the next lesson, we'll cover line integrals, and that would bring us to a very nice discussion on U-substitution once again. And that also allows us to do things like work done, calculate potentials, and electric fields. So that's up for the next video. But I hope you've enjoyed this one. Have a nice day, and I'll see you next time.